Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. We are doing a deep dive today into the semiconductor diode from Unit 14, Semiconductor Electronics. Our mission is to explain this key component so clearly that you lose all fear and are, well, ready to tackle any exam question on PN junction diodes and their applications.
Right, this is where electronics really begins. When you see those diagrams of PN junctions, they can look a bit intimidating. All those terms like depletion region and potential barrier. I think what students really want to know is, how does this tiny thing actually control electricity?
That's the perfect question to start with. Let's think about something you use, multiple times a day, your mobile charger. You plug it in the wall socket, and that socket provides alternating current, AC. Now, this current is a bit chaotic. It reverses its direction 50 times every second.
Okay. But my phone battery needs direct current DC, which only flows one way. If you push AC straight into a battery, it would just heat up and get damaged, right?
It would fail. Absolutely. So inside that small charger box, there has to be some component that does this conversion, this massive, absolutely essential conversion from chaotic AC to disciplined DC. What is that tiny little gatekeeper?
It has to be the diode. We're told it acts like a one-way electrical valve.
Precisely. And here is the really fascinating part, something that seems completely counterintuitive.
Yeah.
Normally, the diode blocks current if you apply voltage in the wrong direction. We call that reverse bias.
Yeah.
But if you increase that reverse voltage a lot, the diode suddenly and very sharply fails, and it starts conducting a large current.
Wait, it fails by conducting? That sounds like a disaster, like a short circuit.
It does sound like it, yes.
Yeah.
But engineers have actually mastered this specific failure mode. It's called Zener breakdown. And they designed special diodes, Zener diodes, to operate in this breakdown region safely. They use this controlled failure to regulate voltage.
So a device that converts AC to DC can also be intentionally broken to stabilize a power supply. Okay, we definitely need to understand the physics of this, the PN junction itself, to see how it can do all of this.
Exactly. So let's establish the core idea first. A semiconductor diode is, at its heart, the simplest electronic device possible. It's just a single PN junction packaged up.
Right, where you have a P-type semiconductor with extra holes and an N-type with extra electrons joined together.
That's the one. And its core function is very simple. It acts as a one-way electrical valve. It allows current to pass easily in the forward direction.
But blocks it in the reverse direction.
It blocks it almost completely. And this simple thing, it really changed the world.
You mentioned it solved a huge problem. What was that about? Older technologies.
Yes, a massive one. Before semiconductors, electronics relied on these bulky, power-hungry things called vacuum tubes, or valves. Imagine huge racks of glowing glass tubes just to run a simple computer. They were fragile, they got hot.
I see. So the tiny solid-state diode came in and replaced all of that. It provided a reliable, compact, and super efficient way to control electricity. That's what started the modern electronics revolution.
That is the why of its existence. Now, to really visualize how it works, let's use an analogy. Picture the diode as a check valve in plumbing. The kind that only lets water flow one way.
Okay, so the water is the current and the pressure is the voltage.
Exactly. So if the water pressure pushes from the correct side, that's our forward bias, the valve just swings open and water flows freely.
And if the pressure tries to push from the wrong direction, reverse bias.
The valve immediately snaps shut, it creates a seal and blocks the flow. This instant direction-dependent action is the whole secret of the diode.
And to picture it mentally, what should we see? I'm guessing the VI characteristic curve is important.
Yes, hold that graph in your mind. The VI curve. In the negative voltage part, that's reverse bias, the current line is just flat on zero. Almost nothing is flowing. But as you go into positive voltage, forward bias, for a while nothing happens, and then you hit a specific voltage, the threshold. And the line suddenly shoots straight up.
Almost vertically, like a wall.
Like a wall. That's a great way to put it. The current suddenly floods through once you have enough voltage to climb that wall. Okay, so now that we have that mental picture, let's get a bit more formal about the conditions for conduction. This is called biasing. And to make sure we use the exact exam language, could you please read how NSERT defines forward bias?
Yes, of course. NSERT says, when an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal, it is said to be forward biased.
Perfect. P side to positive, N side to negative. Just remember PPNN. That's the combination for easy flow.
And what about reverse bias? It says, when an external voltage V is applied across the diode such that N side is positive and P side is negative, it is said to be reverse biased.
Thank you. Now, that brings up the most important question. Why is there a minimum voltage needed to start the conduction? That threshold, around zero point 0.7 volts for silicon, why doesn't it just conduct immediately like a resistor?
This is the real physics of the p-n junction, isn't it? It's because of that depletion region that forms at the junction.
Right. When you join the p and n types, electrons and holes cross over and recombine near the junction. They leave behind these fixed, immobile ions.
Exactly. And those fixed charges create an internal electric field, which in turn creates a potential difference. We call this the built-in potential barrier. For silicon, it's about 0.7 volts.
Let's look at an internal fence that's already there, blocking the charge carriers.
A 0.7 volt high fence, yes.
Okay, so now let's apply our external forward bias voltage. How does that help?
The forward bias voltage is connected in a way that it directly opposes this internal barrier. So the effective height of the fence becomes lower. It becomes V sub B minus V.
Ah, so we are pushing the fence down. So if I apply only, say, 0.2 volts, the fence is still quite high.
It is, so only a tiny number of carriers can make it over. The current is negligible.
But as my applied voltage, V, gets closer and closer to that 0.7 volts.
The barrier becomes very small, and at that point, the floodgates open. Majority carriers rush across the junction, and you get a large forward current measured in milliamperes.
Okay, that makes sense. Now what happens in reverse bias? We've connected the battery the other way around.
In reverse bias, the applied voltage actually helps the internal barrier. It makes the fence even higher. The new height is V sub B plus V.
So we are making the blockage even stronger.
Much stronger. This completely blocks the majority carriers from crossing.
That's why almost no current flows.
Almost. A very tiny current does flow, but we'll get to that. It's caused by minority carriers.
Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now that exponential jump in current, let's talk about that for a second. A tiny change in voltage, say from 0.6 to 0.7 volts, causes the current to jump massively.
So that nonlinear change is the key feature we're using. But it also sounds a bit dangerous. Can't the diode just burn out?
That is a very sharp point. And you're absolutely correct. If you just connect a silicon diode to a battery of, say, 0.8 volts with nothing else, poof, you'll be destroyed instantly. Because a tiny voltage increase causes a huge current surge. That's why, in any practical forward bias circuit, we must always use a limiting resistor in series with the diode to control that current. Now let's connect this whole mechanism back to our first example, rectification. Because the diode conducts easily one way and blocks the other, we can use it to chop up an AC wave.
Ah, so you let the positive half of the wave pass through.
And you block the negative half completely. That's half-wave rectification. You've turned an alternating current into a pulsating but unidirectional one.
And that's the first step for every power supply. That is the single most important job of a standard diode, then.
It absolutely is. Now, let's move on to two silent killers. Two common misconceptions that cost students marks in exams.
Okay, what's the first one?
The first one is about the forward state. The wrong idea is that a forward bias diode is just like a connecting wire, that it has zero resistance.
Because it's conducting easily, students think it's a perfect conductor.
Exactly. They confuse easy conduction with perfect conduction. The correct idea is that even when it's on, it still has that small voltage drop across it, that 0.7 volts for silicon. And it has a small but definitely non-zero dynamic resistance. It's not a perfect wire.
Right, so we can't just ignore that 0.7 volt drop in circuit calculations. That's a very important point.
It is. Now, misconception number 2 about the reverse state. The wrong idea is that a reverse bias diode is a perfect insulator. Infinite resistance, zero current.
I can see why students think that. The check valve analogy suggests a perfect block.
It does. But the correct idea is that while the resistance is extremely high, a tiny reverse saturation current called I0 does flow. It's caused by the few thermally generated minority carriers being swept across the junction. It's tiny microamperes, but it is not zero.
So, to restate that correctly,
That's right.
A reverse bias diode is not a perfect wall. It has a tiny leakage current, and its resistance is very, very high, but not infinite.
Exactly. And that brings us full circle to that Zener breakdown idea. If you keep increasing the reverse voltage, that field across a junction becomes incredibly intense.
So intense that it just rips electrons out of their bonds.
It either does that, that's the Zener effect, or it accelerates the minority carrier so much that they smash into other atoms and create an avalanche of charge. That's the avalanche effect.
And this sudden rush of current is the breakdown.
It is. And the magic is that once it breaks down, the voltage across the diode stays almost perfectly constant at the Zener voltage vis.
So even if the current changes, the voltage is locked.
Locked. That's why it's a perfect voltage regulator. A beautiful example of using a controlled failure for a precise purpose. Okay, to make sure all of this sticks, let's lock in some memory anchors.
A mnemonic for the bias condition would be useful. How to remember which way to connect for forward bias.
Simple. Remember the phrase, PPNN forward, P side to positive, N side to negative.
PPNN forward. Got it. And the magic number for silicon.
The catchy phrase is 0.7 V turn-on silicon diode's magic number. That's the barrier you have to overcome.
And you mentioned a gesture.
Yes. Use your hand as a gate. For forward bias, open your palm and point forward. Easy flow, low resistance.
Okay.
And for reverse bias, close your fist tightly. Blocked, high resistance. Associating a physical action really helps. All right, to wrap all this up, here are 3 essential exam-safe points about the semiconductor diode.
Point 1.
The diode is basically a PN junction that acts as an electrical one-way valve, using the difference between holes on the P side and electrons on the N side.
Okay. Point 2.
2. In forward bias, current increases exponentially, but only after the applied voltage crosses the threshold, about 0.7 volts for silicon, because that's what's needed to lower the internal potential barrier.
And the final point.
3. The diode's #1 application is rectification. That's the process of converting AC voltage into the pulsating DC that is required by nearly every electronic device. To get maximum marks in 12 CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam.
Yes, ProfSam.com. Yes, thank you for joining us for this deep dive into semiconductor diodes. Study hard and all the best.